All right, guys, hello. Hopefully that simulation went well. If you have not done the simulation yet, please exit out of the video and go to your personal homework folder to do the simulation first, which will introduce the topic that we are looking at today, which is isotopes and the frequency with which they occur in nature. So our goal for today is being able to analyze the amount of our subatomic particles in different isotopes and being able to predict the average mass of an element based on the abundance of each isotope. So as a refresher from what we looked at in class, isotopes are going to be variations of the same element. So that means if we have the same element, we have the same number of protons. However, they are going to have different amounts of neutrons, and since they have different amounts of neutrons, that's also going to mean that they have different masses. Are going to look at an example of chlorine. Chlorine has two main isotopes, Cl35 and Cl37. Okay. Those numbers at the top left corner are going to tell us the mass of each isotope. So if we look at Cl35, since it's chlorine, we can look at the periodic table and see that our atomic number for chlorine is 17, which means that we will have 17 protons. That's going to be the same for each isotope because we have the same element. We're going to have the same number of protons because we're looking at the same element. What's going to be different, though, is our amount of neutrons. So to figure out how many neutrons we have in each of these, we need to remember that our mass number is equal to our number of protons plus our number of neutrons. So if we look at our first isotope, Cl35, if our total mass is 35 and 17 of that comes from our protons, that means we need the remaining 18 to come from our neutrons. So we need to have 18 neutrons in Cl35. However, if we look at Cl37, now our total mass is 37, 17 of which comes from our protons. So that means this guy would need to have 20 neutrons. So we can see each of these have the same number of protons but different neutrons. Okay. All right. So if we look at this, we have the mass of each isotope. Cl35 has a mass of 35. Cl37 has a mass of 37. However, if we look at the periodic table, if we look at the number at the bottom beneath chlorine, we're going to see that the mass of chlorine on the periodic table is 35.45. Right. So I know what we're probably thinking. Where did this number come from? It's not the same as Cl35 or Cl37. Where did we get this 35.45 from, and why is there a decimal? The reason why this is because the masses on the periodic table, we're going to call these our average atomic mass. And in order to get that average atomic mass, what we did is we took the masses of all the isotopes of that element and found the average. Okay, so we took the averages, or sorry, took masses of every isotope of a element and found the average. Okay. So even though on the periodic table says that chlorine has a mass of 35.45 AMU, there is no chlorine atom with that mass. We got that 35.45 as an average. Again, there's no chlorine atom that actually has a mass of 35.45. That is just going to be the average mass of Cl35 and Cl37. All right, so I know what you're probably thinking here. 35.45 is not the average of 35 and 75. Where did this number come from? The fact is that atomic mass, that 35.45, isn't just a flat out average. It is going to be a weighted average. You're right, because if we took the average between 35 and 37, we would not get 35.45. The reason why we get that 35.45 is that it's a weighted average, so we take into account our percent abundances of each isotope. And remember, the percent abundance is just how often they occur in nature. So how many Cl35 isotopes do we actually have? How many Cl37s do we actually have? Okay. If we look at this, 35.45 is a lot closer to the mass of Cl35. The reason why that is because there is more Cl35 in nature. So the mass of that isotope is going to be more important and weighted more heavily. Okay? So there is actually an equation that we can use to find our average atomic mass. You're going to want to think about just like how you calculate your grade at the end of the semester to figure out what you need to get on a final to pass the class. So just like when you find your grade, when we want to find the average atomic mass, we are going to take the weight of a specific category, or the percent abundance of an isotope, times how many points you have in that category, or times the mass of that isotope. Okay? And then we are going to add to that however many isotopes of that element we have. So if we have a second isotope, we would add to that the percent abundance of that second isotope times the mass of that second one. And then if we had a third, we would keep following the same pattern. So we're taking how much of that isotope occurs in nature. How much weight are we giving to it? Again, think about your grade. And then we're multiplying it by how many points or how much mass the isotope contributes. And we are going to keep doing that for each isotope that we have. So let's look at an example. Looking at copper. Copper has two isotopes. Copper 63 is 69.17 abundant, and has a mass of 62.9296 AMU. So that is going to be the actual mass of copper 63. Our other isotope, Cu65, is 30.83% abundant and has a mass of 64.927 AMU. And we want to find the average atomic mass of copper. So we are going to just plug these values into that equation above. One thing that we want to keep in mind is that when we are using percents, we are going to write them as a decimal. We're going to write our percents as decimal. So when we look at our first isotope, we can see our percentage is 69.17, or 0.6917. And we're going to multiply that by the mass of that first isotope. Okay, so we'll do 0.6917 times 62.9296. What that tells us is that the mass of this first isotope, the 63, contributes to 69% of our overall mass. So the mass of that first isotope contributes 69% of our overall mass. To that, we are going to add the same process us with our second isotope. So we'll take our percent of isotope 2. So we'll write that as 0.3083. Okay, so the second isotope contributes to 30.83% of our total mass times the mass of our second isotope. The actual mass is 64.9278. Once we have done this for each isotope in our problem, we can just plug this in our calculator, and we should find that the average atomic mass for copper is 63.55 AMU. Okay. This should match what we see on the periodic table. So that is always a good way to double check to make sure that you have done a problem correctly. We're going to look at one more example. In this example, we are looking at lithium. Okay, so we know one isotope of lithium is 7.59% abundant. So 7.59% of all the lithiums are this isotope. And this isotope has a mass of 6.015 AMU. You want to find the mass of our second isotope. Okay. So looking at this, it looks like we're not given a whole lot. We know we're giving the percentage and the mass of our first isotope. That is it. So we can get started by doing our percentage times our mass. So this isotope contributes to 0.0759 or 7.59% of our overall mass. So we'll multiply our percent and our mass together. To that, we want to add the percent our second isotope contributes to our overall mass times its atomic. Okay. In the problem, they don't directly tell us what percent of our isotope or what percent of our lithiums are the second isotope. But we can figure it out because we know our percents always have to add up to 100. So if we did 100 minus 7.59, we would find that our second isotope needs to have a percent of abundance of 92.41%. Okay, so if we use the fact that our percents always have to add up to 100, we can find what percent that second isotope contributes to our mass. So then we would write that as 0.9241, and then we don't know the mass of that second isotope. But then we'd want to set this equal to our average atomic mass. Notice how this problem doesn't directly tell us what our average atomic mass is, but we can find it by looking at the periodic table. So if you don't know your average atomic mass in a problem like this, you can always just look at the periodic table and find it. So if we look at lithium, the number at the bottom, or the average atomic mass, is going to be 6.941 AMU. Okay. Now that we have all this information filled in, we only have one unknown, the mass of that second isotope. Now all we have to do is some algebra to solve. So if we do 0.0759 times 6.015, I'll get this to be 0.456. Okay, then if we want to get that mass by itself, we'll see that we'll need to subtract 0.456 from either side. And we'll be left with 0.9241 times our mass is equal to 6.484. And then to undo the multiplication on our left-hand side, we'll divide both sides by 0.9241. And we'll find that our average mass, our mass of our second isotope is 7.02 AMU. This makes sense because our second isotope is much more abundant. Okay, it makes up 92% of all of our lithium atoms. So that means our average atomic mass, that's 6.941, is going to be closer to the mass of our second isotope because that second isotope is more abundant. So it's going to account for more of our average mass. Okay. So the key thing to keep in mind here is just make sure you use that equation we discussed earlier, where we take the percent of each isotope times the mass, and then add it together for each isotope to equal our average. Whichever isotope is more abundant will contribute more heavily to the average atomic mass. And then it's always good to keep in mind that the average atomic mass can be found on the periodic table, and our percents always have to add up to 100. I hope this helped. Please let me know if you have any questions as you are working.